All right, hello everybody. Welcome back to the Calculus Fun Room, your favorite place to hang out. In this video today, I'm going to discuss derivatives of logarithms with you. So up to this point, we have discussed the power rule, we have discussed the product rule, the quotient rule. We have discussed derivatives of the base E exponential, the base B exponential in general. We have also discussed derivatives of trig functions. So today we're going to discuss derivatives of logarithms. So first of all, if we consider finding, we have the function y equals ln of x, and we're wanting to find, dy dx. Right? What is that for this function? Okay. So in the development or the derivation or the proof of this derivative formula, what we would do in this scenario is we would actually rewrite this function and we would solve for x here. So I would, in essence, e both sides, right? So I would raise the left-hand side to the power of e, the right-hand side to the power of e, and what I end up getting is this expression, e to the y equals x. Now, basically what we're going to end up doing here is using implicit derivatives, implicit differentiation. So in our prior video, we had discussed and looked at problems involving implicit differentiation. So in order to find the derivative with respect to x, what we're going to do at this point is differentiate with respect to x on both sides of the equation, right? So we talked about this in the last video, and we talked about when we're differentiating and we want the derivative with respect to some independent variable, then that's the operator that we use. Right, now here's where the implicit differentiation comes from. And again, just as a reminder from the prior video, this is really a chain rule. So I'm taking the derivative with respect to x, but the variable here is y. Now remember, y really is a function of x. So when I differentiate this expression, the derivative of the outer function is e to the y, and then we're going to multiply by the derivative of the inner function. Right? And that was what we were doing with implicit differentiation. It's really a chain rule. And then now when I differentiate x with respect to x, that's just 1. Right? That's our standard derivatives with respect to the same variable. Okay, so what is the derivative of y with respect to x? Well, that's the derivative of y with respect to x. Right? So this is really, y prime. It's the derivative of y with respect to x. So what we're looking for is this term. We're looking for dy dx. So I'm going to take this term, the e to the y, and I'm going to divide it over to the other side. So what I'm going to have in this case is the derivative of y with respect to x being 1 over e to the y. Now we're not really done at this point, right? Even though we've solved for dy dx in our derivation, remember what we were differentiating was ln of x. And what we have is a derivative, but it's in terms of y. We don't see what the function of x is here. So what we would do in this scenario is remember that, let me scroll back up. Right? We are looking for e to the y. And remember that e to the y is equal to x. Right? So when we rewrote our logarithm, and we took our y equals ln of x, we e'd both sides, and we wrote that as x equals ln of y. So when I come back down here, the e to the y, I'm going to replace with x. So what we have then is we have the derivative being 1 over x. So let me write it this way, because this is the way that we wrote it on the board, right, to begin with. So if y equals ln of x, this was the very first line we wrote, then what we have here is that dy dx is 1 over x. Okay, so there would be the derivation of our formula for the derivative of the base e logarithm. So we have the base e logarithm's derivative is 1 over x. So, let's look at a couple quick examples here. Let's suppose we have, y equals, let's say, ln of x quantity squared. What's y prime? What does y prime equal? So we now know the derivative of ln of x is 1 over x. But in this case, we have a nested function. We're going to have a composition of two functions. We have the composition of the base e log and the square function. So this involves the chain rule here, right? So y prime is going to be the derivative of the outer function. So the outer function is the square. So there's the derivative of the outer, and then times the derivative of the inner function. Now remember, when I do the derivative of the outer, I don't touch the inner. So there's my ln of x. And then now the derivative of ln of x we just discussed was 1 over x. So the derivative of ln x is 1 over x. And we still have this expression we have to carry with us. So in this particular example, we have 2 ln of x over x as the derivative of ln of x squared. All right, so again, in this section, we're adding another function to our tool bag of derivatives. We've talked about the power rule, we've talked about derivatives of trig functions, we've talked about product rule, quotient rule, we've talked about chain rule, and now we're discussing the derivative of a logarithm. Oh yeah, we also discussed exponentials like e to the x and b to the x, any base b. Let's look at one more example here. So let's suppose we have f of x equals, let's say, ln of square root of x. And we want to find f prime. Okay, so if I'm finding f prime, right, keep in mind I'm differentiating ln of, and I'm going to go ahead and write this as x to the 1/2. So this also is a composition, right? So I have the inner function being the root. I have the outer function being the ln. So the derivative of ln is 1 over the input. So whatever's inside here, the derivative of the ln is 1 over this thing, right? So, if we think of ln of squiggly, its derivative, right? Its derivative is 1 over squiggly. Basically, that's what the formula tells us. The derivative of ln of x is 1 over x. However, right, keep in mind we really have a composition. This isn't ln of x, this is ln of root x. So this is my inside function. So when I differentiate the outer function ln, that's 1 over the blah. And then the chain rule says take the derivative of the blah. Right, so there's us using the chain rule. All right, now when I differentiate x to the 1/2, I get, what do I get? I bring the power down, and then I take 1 away. And technically I'm done with my derivative, right? We could do a little bit of algebra cleanup. Keep in mind this is really pushed into the denominator, and it changes the sign of the exponent. So we really have 2x to the 1/2. And then keep in mind, this is really root x times root x, which is going to be just x. So the derivative of ln of root x, we use the chain rule, and we end up with 1 over 2x. Isn't that cool? That's so exciting. All right. So remember the beauty of mathematics, right? The beauty of mathematics ultimately is in the application. So we're gonna take a look at some applications. Also keep in mind that typically in a calculus textbook, this chapter where we discuss derivatives, right? There's two things that we're doing. One is we're developing the skills. We're using the formulas, if you will, right? The shortcut formulas. So we know the derivative of sine of x is cosine x. Right? We know the derivative of e to the x is e to the x. We know the derivative of ln of x is 1 over x. So we build skill, and we use those formulas to find derivatives. But again, as I mentioned in a prior video, ultimately we're applying derivatives to things like rates of change. So we're going to take a look at an example like that in just a minute, but let's keep focusing on the skill for the moment. All right, now we derived the formula for the derivative of the base e logarithm. What if we want the derivative of any base logarithm? So what if I want the derivative of log base 2, or what do I want the derivative of log base 7, something along those lines. All right, so if I kind of pose a question here, we're basically saying if y equals log base b of x, so any base, not just base e, we're looking at base b, right? What is dy dx? So look, in the derivation of this formula, we're going to really do the same thing we did at the very beginning when we developed the formula for e to the x. So what we did here is we wrote this expression. We rewrote this expression. And I'm going to base b both sides. Right? So if I base b the left-hand side, base b the right-hand side, I get b to the y. And then remember over here, these are inverse functions. B to the power and log base b of something, these are inverses. They wipe each other out, and I get just x. So just like in the last example, we want the derivative with respect to x of our function y. So we're going to operate on both sides of this expression, finding the derivative with respect to x. Now, as a quick reminder, what's the derivative of the base b exponential, right? So in the prior video, we talked about the derivative of e to the x is e to the x, and then we talked about the derivative of b to the x being b to the x times ln of b. So we're going to use this version, right, because we have any base b exponential here. So what's the derivative of b to the y? Well, it's b to the y times the ln of the base. And then the chain rule says take the derivative of the y term with respect to x. So again, this is technically an implicit derivative process that we're doing here. We have b to the y, ln of b, and then times the derivative of the inner function. And then the derivative of x with respect to x is just 1. So then we're going to again do the same thing that we did when we derived the derivative of base e logarithm. So what we're going to do in this case is solve for dy dx. So I'm going to divide all of this stuff over. So I'm going to end up with dy dx equals 1 over b to the x ln of b. Oop, that's a typo. This is b to the y here. Let me fix that. And then just like in our initial derivation, we don't want y's and our derivative with respect to x. So let me scroll back up. What is b to the y? Well, b to the y is x. So I'm going to write this as this is x, 1 over x, ln of b. So the derivative of log base b of x is, let me change to red, right? The derivative of log base b of x is going to be 1 over x and then ln of the base. Okay. So we have a more generalized formula for the derivative of any base logarithm. So our first couple examples were base e, and then this now is a more generalized form for any logarithm base b. All right, so let's do a couple examples of this, and then we'll move on to some other ideas. All right, so let's say in this problem we want to find the derivative of, let's say, log base 3 of x. Let's just start with that. Right? So from our formula above, when we had log base b of x, that was 1 over x and then ln of the base. So again, that's just our formula we just wrote where the base is 3. So we get ln of the base. So log of x gives me 1 over x, and then base 3 gives me ln of 3. Let's say we would want to find the derivative of log base 5 of x cubed. So again, this is a chain rule like we will typically see as we move deeper into derivatives. So the inner function is the cube, the outer function is the base 5 log. So when I differentiate this, I'm going to differentiate the outer function first. So what's the derivative of log of blah? Well, it's 1 over the blah times the ln of the base. And then the chain rule says take the derivative of the inside next, right? So the derivative of the outer times the derivative of the inner. So the derivative of the base 5 log of blah is 1 over blah, ln of the base, and then the derivative of the inside. So we can see here, right, derivative of x cubed is going to be 3x squared. So I have 3x squared that's going to go into the numerator times 1. So I'm going to have 3x squared over x cubed ln of 5. And then I could simplify here. An x cubed and an x squared and an x squared cancel. And I'm left with just an x in the denominator, and I have the 3 in the numerator. Okay. So there's 2 examples of using that more generalized form. We could do more examples. Let's do one more, right? So keep in mind that in all of these examples that we're doing here, we've used the chain rule. I want to pick something a little bit different. Let's suppose we do a product rule. So let's say that we want to take the derivative. Let me change variables, right? Let me do the derivative with respect to t. We're going to do t times ln of t minus, let's say, sine of t, something like that. All right, so when we differentiate the independent variable t with respect to t, right, the first thing we see here is a product. Right? So again, the derivative of a difference is the difference of the derivatives. Right? So again, as a reminder, we're pushing the derivative operator over the subtraction sign because that's one of the properties of the derivative operator. And now when we differentiate this expression, it's a product rule. So I'm going to do, let's say, derivative of the first times the second plus first times derivative of the second. So this is going to be derivative of the first times the second plus first, and then derivative of the second is 1 over t. And then we're going to subtract the derivative of sine, which is cosine of t. So I guess in this case we got a little bit of a simplification, right? T divided by t is 1. So we're going to get ln of t minus 1 minus cosine t. And there's the derivative of that function. And again, we're involving a product rule as we do that particular derivative. Okay, I'm going to do one more example here. And then I want to throw a couple problems at you to let you try. All right. So let's do something like this. Let's say we want to find, again, I want to stop using x variables. So let's say we have h of, what do I want to pick? H of s equals the square root of, say, 1 plus log of s. Okay. And what we want to find is h prime. Right? The derivative of h with respect to s. What is that equal to? Okay, so h prime, right? The derivative of h with respect to s. All right, now let me back up a second. So before I take this derivative, right, usually what we do is we rewrite roots as exponents, right? So I have 1 plus log of 5, and all of that is the 1/2 power. So that's what I'm differentiating, right? Always want to write roots as exponents. So now let's take the derivative. What's h of s? My s's are starting to look like 5s here. Let me change that. That's an s. Okay. All right, so when I look at this expression here, this is a chain rule again. So the inner function is 1 plus log 5. The outer function is the 1/2 exponent. So I'm going to take the derivative of the outer, and then 1/2 minus 1 is negative 1/2. And then I'm going to multiply by the derivative of the inner. trying to make my 5's and s's look different there. Oh, wait, that's not log base 5. What is wrong with me, right? Okay, so actually at this point, since I made that typo, let's remind ourselves, right? If I have log and I don't specify the base, right? Remember, that's a base 10, technically, right? So we have log base 10 there. So when I differentiate this log base 10, I'm going to have to use that more generalized form that we developed second. Right? Now remember, when I do the derivative of the outer, right, I just rewrite the inner. So let me just put that guy there. That's an s. All right, so now when I differentiate this term, right, the derivative of 1 is going to be 0, and then I'm going to differentiate this logarithm. So this derivative, right, is 0 plus, and then what's the derivative of log base b of the variable? So it's 1 over the inside, and then ln of the base. So again, log base b of blah is 1 over the blah times ln of the base. All right, so anyway, this 0 is really redundant, right? What I really have here is just that guy as the derivative. So I have, in this case, right, I'm going to push the root into the denominator. So I have 1 over 2 square root of 1 plus log of s times, then I have 1 over s ln of 10. So there's my derivative of my function. My fingers do not want to work today, of h prime of s. I mean, I could multiply these together. Usually in a solutions manual, we're going to see this as one big fraction. So I have 1 all over. I have 2. I'm going to write the numbers up front. So I have 2 ln of 10. Those are like coefficients. I'm going to take the s next, and then I'm going to write the root of 1 plus log base 10 of s. So there is our final version of our derivative. Okay, so what I want you to do next, I want to do kind of like a summary of everything that we've done up to this point. Some level of summary here, kind of like a review. So I typed these problems out and put them up here. And what I want to do is, have you pause the video. I want you to try each of these on your own. And then when you're done trying each of these on your own, unpause the video and we'll talk about these together. So go ahead and pause the video, write these down, and attempt all 7 of these. All right, so now that you have attempted each one, let's take a look at these together. So number 1, we're looking at something that is, polynomial. Right? In other words, we have a variable in the denominator. We have the exponent as a fixed value. Right? So that calls for the power rule, right? So if we have the variable as the base, I think I said denominator a second ago. If we have the variable as the base, we have a fixed number as the exponent, right? Then the derivative of that is a power rule, right? So I'm going to do a power rule here, right? So y prime is going to be 2x to the 1. All right, let's take a look at the second example. So the second example, we have the reverse relationship. Notice that the variable is now in the exponent. The base is a fixed value, right? So we basically have that relationship. The base is a fixed number, the variable is in the exponent. So when we differentiate that form of an exponential, we have b to the x times ln of b, right, is our formula. So when I differentiate 2 to the x, I'm going to have 2 to the x times ln of 2 as my result. And the reason that I picked these first two was for us to focus on how we know when we're using the power rule and how we know when we're using like an exponential rule, right? And again, the idea is, where's the variable? Where's the fixed constant value? So let's take a look at the third one. So for the third one, we have y equals e squared. So notice in this scenario, we don't have any variable here. Well, I mean, we have the y variable. We don't have any x variable over here. So in other words, this is constant. And if you plug e squared in your calculator, you're just going to get some decimal value. So we have really, the derivative of a constant. That's really what we have. And what's the derivative of any constant? That is 0. So our derivative of e squared is just 0. Why is my pen being mean to me today? All right, so let's take a look at number 4 here. So in number 4, we're going back to really, I think this was our first example we did, or something like this, right? So we have ln of x squared. So we really have a power rule here, right? We have the x as the base, and we have the fixed constant as the exponent. So this is a power rule, but keep in mind it is a chain rule. So it's not just x squared, it's ln x squared. So the square is the outer, the ln x is the inner. So I'm going to take the derivative of the outer, and then I'm going to multiply by the derivative of the inner. So I'm still doing a power rule here, variable base, fixed exponent, but it's a chain rule. All right, and then the derivative of ln x is 1 over x. Right? So I have 2 ln of x times 1 over x, and then we're going to write that in a simplified form, 2 ln x over x. Okay. All right, let's take a look at number 5. So my page is getting out of whack here. All right, just push that down to the top of the next page. So in this example, right, notice that we really have an exponential function. The fixed number is in the base, and then the variable is in the exponent. So again, we're really using the rule of like b to the x, right? Its derivative is b to the x ln of b. Right? But our exponent is not just the simple form x, it is a logarithm. So we really have a chain rule. We really have the base 2 exponential composed with ln x. Right? So the base 2 is the outer function, ln x is the inner function. So when I differentiate the outer, the base 2, I have 2 times, right, 2 to the x, but what we really have is ln there. Right? So we have derivative of 2 to the u is 2 to the u, ln of 2, and then we have to multiply by the derivative of the inside, right, the logarithm. So here's the derivative of the base 2 exponential. Here's the derivative of the inside. Again, this is just 1 over x. So I'm going to have 2 to the ln x times ln 2, and then 1 over x. All right, isn't this exciting? All right, so the reason I have picked these examples so far is for us to be able to distinguish really what is exponential, what is, power rule. Okay, so when we look at this one, again, same type of analysis. The variable is in the base. The exponent is just a fixed number, right? Again, if I plug ln of 2 into a calculator, that's some decimal value. So variables in the base, number in the exponent. This is a power rule, right? So I'm going to bring the power down, and then I'm going to take 1 away from the exponent, and there's my power rule. All right, now let's take a look at number 7 that we had here. So if I'm differentiating ln of 2x, right, again, this is just ln of a function. So I'm doing the logarithm rule formula, if you will. So the ln of blah is going to be 1 over the blah times the derivative of the blah. The derivative of 2x is just 2. And then in this case, the 2's will cancel out, and we're just going to get 1 over x as the simplified version. All right, hope you did well on those. If you didn't, that is totally okay. It can be a little confusing to identify what's exponential, right? What's power rule, and it just takes practice. And that's why I wanted to put these in our activity here so that we could have those conversations about how to identify those. Okay, let's take a look at this next problem. Now, in this section where we talk about derivatives of logarithms, one of the last things we discuss is what we call logarithmic differentiation. So I want to build up to what logarithmic differentiation is. I want to do this kind of in a exploratory manner. If I was giving this in my a face-to-face course, I'm going to hand this problem out and I'm not going to say anything. So we would have talked about those prior 7 problems. I would have handed this out and had students in groups attack this problem. So let's just work through this together here and discuss what we would do when we come back together and review this. Feel free to pause this video and work on this on your own. That's probably a better thing to do here. And then unpause the video and we'll go over this together. Okay, so you've tried this, you've unpaused the video, let's talk about this together. So here's a function, y equals x to the sine x. And the question is ultimately that we want to take the derivative of this function. So letter A, I ask, why can't you use the power rule? So keep in mind, the power rule needs variable in the base, fixed value in the exponent. I need a fixed number here, and I don't have a fixed number in the exponent. I'm going to say, the exponent is variable, let's say. We can't have both places having a variable. Why can't we use the derivative of an exponential formula? Well, again, an exponential wants something like this. It wants the base to be a fixed value. My base is not a fixed value, right? Base is not, let me call that constant. So how do we take the derivative of this expression? Well, there's 2 ways we can do this. I want to work through one of them, and then I want to come back and talk about what we call logarithmic differentiation, which is a little bit quicker of a process. So first of all, keep in mind that we can rewrite this function that we're differentiating, x to the sine x, as e to the ln of x to the sine x. Right, and usually students in a class will say, wait, why can I do that? Well, remember, e and ln are inverses of each other. So if I have, like in an algebra class, e to the ln of x is going to be just x. The e and the ln undo each other. They're inverses. Right? So whatever's inside the logarithm basically drops out as the e and the ln undo each other. And I'm just going backwards here, right? E to the ln, those are going to wipe each other out, and then x sine x is just going to drop out. I'm going backwards. So I'm taking x to the sine x, writing it as e to the ln of x to the sine x. Now I have a property of logarithms. One of the properties of logarithms is that if I have an exponent inside the logarithm, I can pull that exponent in front of the logarithm. Now, I don't want to get back into an algebra discussion. There's 3 properties of logarithms that we learn in an algebra course. This is one of the 3. I call it the power rule. There's also the sum rule, or the product to sum rule, and the quotient to difference rule. This is the one we're using here. So I'm going to take this exponent of sine x and I'm going to pull it in front as a coefficient. So I'm just using this rule. The exponent moves in front of the ln. Exponent moves in front of the ln, and we have this expression. So what we have done here is we have effectively taken an expression where we had a variable in the base and in the exponent, and we now have a fixed value in the base. So this is exponential. I can now use the derivative as a base e exponential here. So differentiating this function will be equivalent to differentiating this function. So let's differentiate e to the power of sine of x times ln of x. All right, so the derivative of e to the blah is e to the blah, and then times the derivative of the blah. So I'm doing a chain rule here, right? I have a composition and I'm doing a chain rule. Now when I take the derivative of the exponent, this is a product rule. So let me give myself a little bit more room here. So what is the derivative? So let me carry this guy down. I have e to the sine x times ln x, and let's differentiate the exponent. So let's say derivative of the first, derivative of sine is cosine, times the second, which is ln of x, and then plus the first times the derivative of the second, which is 1 over x. So there's the derivative of my exponent, for my base e exponential. And technically, we are done with the derivative at this point. However, I'm going to do a little bit of cleanup. So remember that e to the sine x times ln x we have up here. E to the sine x times ln x was really our way of writing x to the sine x. So this guy right here is really x to the sine x. And then we have cosine x, ln of x, plus, let's call that sine x over x. And there's our derivative. So in this example, the function that we had was not a power rule. It was not an exponential rule. However, we did some creative algebra, taking blah and writing it as e to the ln of blah. And then we use the property of logs to simplify. So we end up with a base e exponential. We differentiate that base e exponential, and we get a formula for the derivative of x sine x. All right, so in a scenario where I can't use a power rule, in a scenario where I can't use an exponential rule, so in other words, when I have a function to the power of a function, this is one approach to take here. So just as a summary real quick, if I'm differentiating, let's say f of x to the power of g of x, right? So I have variable in the base, I have variable in the exponent. I mean, what I would technically do first is rewrite this as e to the ln of f to the g, right? And then what I do is, I'm going to run out of digital paper here, right? I pull the g in front of the logarithm. All right? And then here's what we're actually going to differentiate. We're going to differentiate the exponential, I'll say, continue, just like we saw in that example. So one process here is to algebraically manipulate the function of x to a function of x. Another process, which is a little bit more efficient, is what we call logarithmic differentiation. So let's take a look at what logarithmic differentiation entails. So again, I want to come back and let's use our function that we were looking at for this example. So let's look at y equals x to the power of sine x. What is going on with my digital paper? All right, so y equals x to the sine x. So here's what logarithmic differentiation says to do. So instead of taking this expression and writing it as e to whatever, what we're going to actually do in this case is we're going to ln both sides of this equation. So if we have an equation that y equals something, right, I'm going to ln both sides of the equation. Now again, the only time I'm going to do this is when I can't use a power rule and I can't use an exponential rule. So I ln both sides, and then on the right hand side I'm going to use that property of logarithms, which says I can take this exponent and pull it in front of the logarithm. So I'm going to write this as sine x times ln of x. Keep in mind it's sine x times ln x, and then I have ln of y. Now at this point, all we've really done is some algebra manipulation. We've logged both sides, and then we used a property of logarithms. So now I'm going to finally do the derivative. So I'm going to differentiate the left-hand side, and I'm going to differentiate the right-hand side. Okay, now on the right-hand side, all of the variables I have are x's, and the variable I'm differentiating is x's. So this is just a standard product rule. Derivative of the first times the second plus first times derivative of the second. Now when I look at the left-hand side, the variable I'm differentiating is x. The variable in my expression is y. Now again, this is an implicit derivative technically because y is a function of x. Remember, y equals x to the sine x. So y is a function of x. So what's the derivative of the outer function? It's 1 over the inside, and then we multiply by the derivative of the inside. And this is what we're looking for. We're looking for the derivative of my y function with respect to x. So what I'm going to do algebraically is to solve for this term, I'm going to take the y and multiply it to the other side. So I'm going to have, y prime equals, and then I have y times that expression Oops, let me just write that as sine x over x, okay? And then we're really done at this point, except we'll replace y with its function. So the function we were differentiating was x to the sine x, right? That was y equals x to the sine of x. So we're just replacing what the y is, and that multiplies all of this stuff inside. And there's our answer. That was the same answer we got from the first process. So the reality is you could use either process here. If you have a function of x raised to the power of a function of x, can't do the power rule, can't do an exponential rule. Two different approaches to take here. First approach is to rewrite the function. Second approach is to ln both sides of the equation. And the second approach is what you would see in a textbook called logarithmic differentiation. All right, I think that's everything I want to discuss with you here in this section. Now, keep in mind, up to this point now, we have a lot of different functions in our tool bag that we're differentiating. We're differentiating things like x to a power using the power rule. We're differentiating things that are exponential, like e to the x or b to the x. We're using the product rule. We're using the quotient rule. We've taken derivatives of trig functions, sine x, cosine x, tangent x. And we've talked about derivatives of logarithms. So in the next couple of videos, what we'll take a look at is how to apply all of this stuff, right? So we have started focusing on skills for the past couple videos. We're looking strictly at skills, how to differentiate these different types of functions. But again, the big picture here is the beauty of math is why do we do this stuff? And it's for rates of change. So in the next couple videos, we'll focus again on big picture and we will look at the why.